everyone, how's it going? And welcome to Community Conversations. My name is Liz Yang from the Divinity Foundation. So Community Conversations is an opportunity for you, the community, to hear from contributors within the internet computer ecosystem, as well as ask some questions live. So today we will give an update on the current status of Canister Sandboxing implementation with Senior Software Engineer Adam Brachke, Research Scientist Helga Baumann, and Principal Software Engineer Ulan Degenbayev. So we're going to kick things off with Helga. So feel free to take it away, Helga.
Yeah, hello everyone. So this is a brief update on the status of the Canister Sandbox. We had a community talk already about this when we had this originally. We talked about the project plan, and now this is actually nearing some milestone conclusion, namely that there's an imminent launch of the first version of this. First, we'll give a bit of recap what we're trying to achieve and overview of Canister Sandboxing, then a bit more details on how the actual communication works. There will be a project update on the performance and how things generally work and what things we did to optimize, particularly shared memory. Adam will then talk about further optimizations on the system API, how to structure this for a very efficient sandboxing, and also give an outlook on the rollout plan and some future work that is still needed that we want to follow up with to achieve the best possible sandboxing for the internet computer. So what we're talking about is the Canister Sandboxing, which is at the innermost layer of the IC, namely inside the execution layer. As such, it is not a user-visible feature, and you will actually hopefully never get in contact with it, because the only reason you will get into contact with it is if it breaks, and it hopefully never breaks. It's a preventive measure to make sure that there is no security disaster that's happened, and with all preventive measure, you also generally don't see it happening, because if it does its job, it's preventive, then actually no security incident happens. So the security threats that we are addressing with regards to WASM execution are manifold. The most severe kind of security threat is an actual bug somewhere inside the WebAssembly runtime, the compiler, somewhere in the system calls, or the glue code to hold it all together. Because if there is such a bug, then there is a quite good chance that it means that an attacker could bypass security restrictions imposed by the WebAssembly runtime. And what this could allow an attacker potentially is to execute arbitrary code on the internet computer in the context where the WebAssembly is running. Could also allow access to arbitrary internal data structures of the process hosting the WebAssembly. The second kind of threat is a bit more subtle. This is side channel attacks, and this does not require any actual bug inside the WebAssembly runtime. It is a nature of the fact that if you're executing code on a remote system, you always have the opportunity to interact with the microarchitecture state of the CPU. And depending on the circumstances, it is possible via cleverly crafted measurements of this to extract data that should not normally be accessible to the code, but still get some measurements and extract some information of it. So this is referred to as side channel attacks, and to both threats, there is actually a common solution, and this is process sandboxing, namely confine all the WebAssembly execution into a process of its own and ensure that this process is sufficiently shielded from the rest of the system that none of the above problems actually leads to any impactful penetration into the internet computer. So this is an established project. This has been many times before in different contexts or in different other contexts. So we are also using well-established technology here. So on the next slide, I'm trying to depict the actual security setup of the system. What we will be doing is to actually confine each canister into a process of its own. So whatever canister is installed on the internet computer, it will run, all of its WebAssembly will run in a process by itself. So in the system, we will, a bit simplified, but we will roughly have the replica process on the upper left-hand side. We will have the individual sandbox processes, those colorful blocks in the middle. And of course, we have other entities in the system, like the actual operating system kernel, the big at the very bottom. And there's various security isolation layers that we need to put into the system to achieve the security goals. So for one, we obviously are shielding all the sandbox processes from each other. So one sandbox cannot interact with any of the other sandboxes. Secondly, the sandbox processes cannot interact with the replica except for a very narrow and well-defined channel that is an IPC socket, an ICP communication socket between replica and sandbox process. It's an individual socket that the replica has with each of its sandbox processes. Additionally, also we need to protect the rest of the operating system from the sandboxes and isolate them. There is some access possible to resources that it needs for operation. I'll come to that a bit more, but critically, we are disallowing any other kind of interaction that is not absolutely necessary for operation, and this is, of course, to protect the entirety of the system from a potentially compromised sandbox. The resources that are accessible are twofold, and these are on the one hand checkpoint files, and on the other hand the modified memory pages. Both are kind of realized as shared memory segments that are shared between the sandbox process and the replica, so both can access these. But each sandbox can only access its own shared memory segments. It cannot access the shared memory segments belonging to other canisters, while the replica has the whole picture and can access the memory of all canisters. There's a security policy in place that does all of this enforcement, and where there's machinery that ensures that, and we're using various techniques to make the resources accessible. So, for example, the files that are accessible there, the canisters do not open, the sandboxes processes do not open them by themselves, but actually it's mediated by the replica. The replica actually passes handles to them so they can be opened, and the sandbox processes cannot actually directly access them by themselves. On the next slide, what we're trying to achieve is that we have a particular threat model in mind. Namely, what we assume is that an attacker can gain complete control over the sandbox process that is running a canister. But we also assume that the only one who can do this is the actual author of the canister code, because we're assuming any such compromise requires specifically crafted WebAssembly code, and of course only the owner of the canister can decide what code is actually running in that. And with this threat model in mind, the attacker has, of course, the capability to do anything that this process can do inside the system. And on the next slide, exactly, we want to show what we actually want to guarantee. Namely, we want to guarantee integrity and confidentiality of the remainder of the system to the best extent possible. So assuming the red canister sandbox process is compromised, what we want to guarantee is that the canister depicted in green here, that all of its data remains confidential and remains unchanged by the compromised canister, so it cannot change, neither change nor see the data. There's also metadata for this, for the compromised canister, for example, like accounts balances or message queues or something. These are still off limits from the compromised sandbox. That means, of course, actually each canister can inspect its own message queues and cycle balance and such, but it can still not tamper with it. So one thing that would, for example, still not be possible, that compromised sandbox could mint arbitrary amount of cycles. We also want to protect against. There's one limitation to the threat model that we also want to mention. While we are guaranteeing integrity and confidentiality of all the data in the IC, we may not be able to fully guarantee availability. And this has to do with the fact that if a sandbox is cracked, then of course, attacker can do arbitrary things with it. And what they can, of course, cause is state divergence with regards to all other nodes. And if a sufficient number of nodes in a subnet are compromised, then the state divergence may cause the subnet to stall. But this is only temporary, because if the canister is quarantined or is expelled from the subnet, then actually the state also is perfectly in sync again, and the subnet can continue. So this is a possibility that we cannot rule out by sandboxing alone. There might be other techniques needed to prevent this automatically, but again, it is only a temporary measure, and there's still no lasting effects, even in this attack scenario. Okay, let's have a look at the actual interaction between the replica and the sandbox. As I said, there is one backend process per each canister. And the sandbox processes are structured such that they take over the WebAssembly execution, and they of course need all resources that are required to run the code. And if we look at what a canister comprises of, there is, from the user perspective, the most important thing is actually the execution state. This is all the user accessible state of the canister. This includes the WASM code itself. It includes the stable memory, and includes the WASM memory that the system uses. There's also a companion system state to each execution state, which is the system level view. This comprises message queues. These are things that are not directly accessible to the canister, but to the user code, but there's a restricted API access to this. What we do is that the replica will spawn a sandbox process and make the resources available in the sandbox, and then trigger it to running the code. To see the actual interaction in these two diagrams, we have to distinguish between two different kinds of calls that we can. First is a kind of cold call. This is basically when the system has booted up and a canister has never executed on a particular replica. Then what the replica will have to do is we'll have to spawn, obviously, the sandbox process, and then set it up such that it can execute. It will send down the WebAssembly code. It will send down the WASM and stable memory. Subsequently, it will start the execution, and when the sandbox executes, after it has executed fully, it will, on the one hand, report back to the replica the completion and any output of the computation that happened there. What the sandbox will also do, it will inside itself create the post execution state representation. So if there's changed memory, it will create a representation of that changed memory such that this already exists in the sandbox. And the significance of this is can be seen in the diagram on the right-hand side. Namely, if we do any subsequent calls, then the sandbox is kind of hot already, and that means when the replica needs to execute something on there, it can start execution. It will not upload any code or any memory anymore because the state already exists on the sandbox. The sandbox will report the completion and also create its post-execution state in its process, and will report to the replica. The replica gains all information to also create the same state that is in the sandbox, so that replica and sandbox again have a precisely mirrored view of the state of the canister. In a sense, this scheme is optimal because we have only a single round trip, amortized single round trip for every call. So it's not really in principle possible to do anything better than that. And the amount of data that's transferred is really size of the input, size of the output, plus a representation of the diff. We are not sending actual memory data around here. A diff is really just a logical representation of the diff. Yeah, that actually is a nice handover to Ulan, who will talk about precisely that, namely how we actually optimize the state representation.
All right. Yeah. Thank you, Helge, for introduction and also for explaining how sandboxing works on the high level. Let me start with giving an overview of what happened since our last community conversation where we kicked off this project. At that point, we had the initial prototype implementation that Helge developed. It was functional, but it was slow and it was missing some features. Also, like integration with the system and infrastructure was missing, as well as security policies. And our goal was to take this prototype and make it ready for production. Overall, we spent around 9 software engineer months on this project. We did about 100 commits, added 25,000 lines of code, removed 15,000 lines of code. And at this point, we think that the Canister Sandboxing is ready for like initial launch. And I'm going to give like details on like interesting parts of the project. And the most interesting is performance, because performance was the main blocker for the prototype. And in this graph, you see why. Like the graph shows the throughput on one of our benchmarks that is doing memory intensive work, and how the throughput improved over time. So the benchmark, we call it memory canister. It simulates the queries that are doing some non-trivial amount of work. So what it does, it copies 5 megabytes of data from one memory location in WebAssembly to another. And the initial prototype was very slow. It could do like one query in 10 seconds. Then in December, we implemented the initial version of shared memory, and that gave us a huge boost in performance, but there was still gap. And in January, we iterated on that, like implemented more optimizations. And by now, the performance on queries or like requests that do some amount of work, non-trivial amount of work, looks good. We also have another benchmark, which we call a counter canister. So this counter canister exercises a very lightweight load, where each query executes only a couple of instructions. So basically what this benchmark is doing is it measures the overhead of the system, like how long it takes us from getting a query to entering the WebAssembly engine, like immediately exiting it and like responding the query. The initial prototype was 2 times slower than the baseline, like the non-sandboxed version. And all of this performance difference was caused by the overhead in the IPC, like interprocess communication. And like in 3 months, we've been improving the interprocess communication, optimizing it. And we are like at point where we don't find any like obvious optimizations, and there is still 550 microseconds overhead for this IPC communication. So in percent, it translates to about 30% regression compared to the baseline. And while we were analyzing like performance of the queries and all the IPC mechanism, we found another optimization opportunity, and that is like improving the query pipelining. And that gave us enough performance improvement to catch up with the baseline. The caveat here is that this optimization also applies to the non-sandbox version, so it works in both versions. So this means that the baseline also improved with this optimization. But nevertheless, we are quite happy that we at least don't regress the old baseline with the sandboxing. Few more interesting numbers for performance, like in our local measurements, we see that it takes about 10 milliseconds to start a sandbox process. So this is the cold case that Helga described. And this overhead of 10 milliseconds applies only to the first request of the canister. All subsequent requests will not have this overhead, but there is still like the 150 microsecond IPC overhead that still remains. We hope that in future we will be able to improve this more. In terms of throughput, like it depends on the workload. On some workloads, we see that the throughput is similar to the baseline. In other workloads, like there is up to 10% regression that we observe. In terms of latency, it's either similar or like up to 30% regression. And this 30% regression is exactly the case I described as the counter canister, where the queries are very lightweight. The memory overhead that we see locally is about 2 megabytes per sandbox process, but this one is very dependent on workload. Now, Adam and I will describe the two most important optimizations. The first one is optimizing the memory representation. So the initial prototype used very simple and obviously correct scheme where for each request, like query or update, it would send the whole content of the memory to the sandbox process. Sandbox process executes and then returns back the modified pages. So this works and it's simple, but the downside, it's very slow. What we implemented is shared memory so that both processes can use the same memory pages. And to show how it works, I need to go deeper and explain the memory representation and how it maps to WebAssembly instance memory. So each canister memory consists of two parts. Like one is the checkpoint pages or checkpoint file. This file stores the content of the memory of the canister at the last checkpoint. And then all the modifications that happened from the last checkpoint until the next checkpoint, they are accumulated in this kind of overlay layer that's kind of a tree-like data structure that stores all the modified pages. We call it page delta. And together, these two parts then produce the actual WebAssembly memory. Now, to share these pages, what we need that these pages are backed by some file. And then once they are backed by a file, we can memory map the file to Replica process and to Sandbox process and thus share the memory. For checkpoint pages, this is simple, right? Because we already have the checkpoint file. But the modified memory pages, they were allocated in the Rust heap, and there is no file, no backing file, and it's very difficult to share the Rust heap memory between two processes. So what we did is we implemented our own allocator, and this allocator is optimized for exactly this use case of allocating pages, and it's backed by a file. We call it page allocator file. And what it allows us is that now we can share the memory. So we have the checkpoint file, page allocator file, and then we can map these files to the two processes. And the processes can now exchange memory pages by not sending the contents of the pages, but just sending the offsets of these pages in the files, which is much more efficient. And this optimization allowed us to close the performance gap in the memory benchmark I mentioned earlier. And now Adam will tell us about another important optimization.
Yeah, so this is about the optimizations we did with regard to the system API, which is basically the interface we provide for canisters to do various things like the examples given here, like read and write to their stable memory, the memory that persists across upgrades, or call another canister, or move cycles from your own canister's balance to a message you're going to send to another canister, some things like that. And in our initial prototype, we didn't want to just give the sandbox process complete control of its system, the state of its system state, because then a canister that breaks out of WASM time could just do anything, including giving itself a huge number of cycles. So in our initial prototype, each time a canister wanted to make modifications to its system state through one of these system API calls, it would have to send a message over the IPC Helga described to the main replica process, which would handle that call, make sure it was valid, and reply to the sandbox. And this was just not performed enough. It had way too many round trips through the IPC. Being the next slide, go on. Okay, so the way we changed this was we would, at the start of the message, send all this information about the system state over to the sandbox process, which would keep its own copies of those and would then be able to handle all of the system API calls directly within the Sandbox process. And then at the end could send all the changes that need to be made back to the Replica process, which would then update the Canister's system state. But we can't, there's some issues with this, namely what I was describing before, where a canister that's able to break out a WASM time could just tell the Replica at the end that somehow it ended up with, you know, 1 million more cycles than it had before. So we need to basically verify the updates that we're getting from the Sandbox, make sure they make sense. And so we have some basic checks there to make sure that the canister or the Sandbox process didn't do anything illegal before we actually apply those changes to the system state. Yeah, go to the next slide. So now that we have everything ready to roll out, this is the plan for what we're going to do. Phase 1 was just enabling sandboxing internally within Dfinity so that everyone would run their tests with sandboxing enabled, and all our pipelines would run with sandboxing enabled. And we were doing that all last week, and we didn't really see any problems with that. So now we're about ready to move to phase 2, where we'll enable sandboxing just on a single subnet, K44FS, which is one that is handling some load, but it's not the biggest one or anything. The proposal to elect this binary has already gone through, I think sometime late last week. It's proposal 40908 if you want to take a look at it or the code. And you'll soon see later this week, I think you'll see proposals to actually deploy that binary to K44FS. And then assuming that goes well, next week, we'll actually enable it on the release we plan to roll out as part of our normal process. So once that one's approved and the proposals go through, it'll just get slowly rolled out to all subnets as part of our normal rollout process. And then phase 4, which we should do afterward, is make further changes to the OS images to more strictly enforce the boundaries on the Sandbox process. So currently we have we don't have all the boundaries in place, but we still get benefits from the fact that the Sandbox is actually running in its own separate process. You get all the natural process boundaries, but we have some extra constraints that we'll add over time afterward. Next slide. So this is a bit about the experience for developers who are working on the IC. So if you're checking out our code, trying stuff out, playing around with it, running tests and stuff, you'll see some slight changes now that we have sandboxing enabled. So the issue here is just that any test that's actually going to be running WebAssembly now needs to run it within a sandbox. Oh, sorry, I forgot to say, so far it's only enabled on Linux only. We're using some features in the sandboxing that need some tweaks to also work on Mac OS. So at the moment, if you're writing tests on Mac, everything will be the same. If you're running them on Linux, you'll see these changes. So if you're running any code, any tests that actually run some WebAssembly, they'll need to have this Canister Sandbox binary built to run the test. This is the executable that we actually run in the Sandbox process. And Cargo, the Rust build system, which we use, doesn't actually have support for that at the time. So we need some way to basically ensure that this binary is built and up to date whenever we run tests. And our current solution is basically when we're running a test, when we need to execute Canister code, we sort of check if we're in a test environment. And if we are, we rebuild that Canister Sandbox binary, which means that some tests, the first time you run them, may be a bit slow at startup because before the actual test runs, it will actually be building some additional code, which you didn't build for the test itself. So if you see some tests taking a little more time on startup, that's where that's coming from. And in the future, we may replace this with a setup where we use like a wrapper script around cargo test or something that'll do the build separately outside of the test itself. You can go to the next slide. So yeah, future work, additional things which we'd like to get to. Yeah, one is speeding up the communication between the replica and the sandbox process. Basically just like so some of the information that's going back and forth or come from types that were designed before we had sandboxing in mind, and they could probably be redesigned to just be more efficient in the context of sandboxing. We want to add some more metrics and logging of what's going on within the sandbox process itself. Compilation in a separate process. So currently the Canister Sandbox is responsible for compiling your WASM code to machine code and then running it, which means that we're giving the sandbox permission to run code that it has itself generated, which if there are some holes in WASM time or something, just makes them easier to exploit. If we had a separate process compile and then the sandbox was only responsible for running it, then we could basically restrict the sandbox process from running code that it itself has written out. So that would give us like even an additional layer of security. So that's something we'd like to look at in the future. Further latency optimizations. Yeah, we have some latency basically when executing a message in the sandbox from like from our basically from our thread context switch would take a little bit of time, which just means that like the full time on a single message can be a bit slower than we could probably make it. Dynamically starting and stopping processes. This is about basically at the moment when you execute a message on a canister, we're going to start up a sandbox process for that canister, and then it'll just stay running for an extended period of time. And ideally, we could probably, at the moment, we can probably handle all these processes running, but as we get more canisters, we can probably get some efficiency gains by stopping sandbox processes for canisters that aren't handling many messages, and then just start them up again if a message happens to come in. So we don't have a bunch of these processes sitting around for canisters that aren't doing much. And then lastly, yeah, we'd also like to get some version of the sandboxing also enabled on Mac OS. As I said before, the current solution is like Linux only, and it will require some tweaks to work on Mac. Yeah, that's all. So I think we can handle some of the questions now.
Cool, awesome. Thanks guys so much. So from the chat, I just saw one question, but if anybody else has questions they want to ask, now is your opportunity. So the one question is from Matthew, and he was asking if the canisters use LXC.
This is probably referring to the isolation layers amount. So, for those who don't know, LXC is Linux containerization technique. No, this is not used. And what we actually use is a very restrictive SE-Linux policy. The policy is relatively short, 80 lines of code or something, if I'm not mistaken. Which is good because this is actually everything that's allowed, everything that's not mentioned is explicitly forbidden. So it's actually extremely restrictive. It is much more restrictive than you could do with containerization. Actually, containerization is also a bit of a two-edged sword. So actually, I think yesterday was published a CVE 2022 0185. I'm not sure if I got the number right, which is actually an exploit relying on user namespaces, which is the very thing used on in containerization, creating mount namespaces, abusing the mount API. So it's actually not that straightforward to say, okay, well, we put this into a container and then it's secure. This is actually, unfortunately, not the case, but there is a lot more thought involved in really making sure that it is, and really restricting the APIs as much as possible. It is possible that at some point we will use additional methods than what we are presently using in addition to the SUNS policy, not ruling out that we use containerization, not ruling out that we might use, for example, seccomp DKF at some point or anything else, but for now it's really just a type enforcement, a very restricted type enforcement.
Thanks so much, Ulan. I don't see additional questions in chat, but unless someone moves really quick and drops something in chat, I think that we can end the call for today. So big shout out to Helga, to Ulan, to Adam for preparing an update on the Canister Sandboxing implementation. Looking forward to seeing what comes next, and see you guys all at a future community conversation. Thanks everyone. Bye now. Take care.